Alright, we've got another example of integration by parts. If this is going to work, I need to differentiate part and integrate part. And I choose to differentiate the x to the fifth because that gets simple and it's easy to integrate or differentiate e to the 3x. So I'll just put it over here. Now, let's see. If I differentiate, remember you're always trading in the integral of one horizontal line for a product and then the integral of the next horizontal line down. You can keep trading in as many times as you like until the bottom row is simple or it repeats what you've done before. We'll look at an example of that later on. So here's x to the fifth. We take the derivative. We get 5x to the fourth. And a derivative of e to the 3x would be 1/3 e to the 3x. Make sure you remember that when you take the derivative of e to the kx, k comes down, right? So we have this 1/3 here ready to catch that. Okay, now that is still going to be difficult to integrate, so I plan to apply integration by parts again. Bring the 4 down, we get 20x cubed, and integrate this gives us 1/9 e to the 3x. Still going to be hard to integrate this horizontal product, so I'll differentiate again and integrate in the other column. Keep going. Okay, differentiate again, we get 120x and 1/81 e to the 3x when we integrate this side. Differentiate 120x gives you 100. Integrate gives us 1/243 e to the 3x. And differentiate one more time, this becomes 0. And let's see, 3 times 243 would be 729. So 1/729 e to the 3x. Whew. I've done this over and over and over again. I can see integration by parts is going to let me trade this integral for this product minus that integral, right? And then I'll trade that one for this product minus that integral. I'll trade that one for this product minus that integral, and so on down to the very bottom integral is going to be particularly easy because I'm going to have the integral of 0, which will be a piece of cake. Okay, just remember that every time you apply integration by parts, you get a negative sign in front of the integral. So the first time you apply it, you get a negative in front of the integral. The second time, you get a negative negative, which makes it positive, and so on. So to keep track of that, we'll just make a little mark out here. Plus, minus, plus, minus, plus, minus, plus. Okay, I put them in circles so I remember that I actually did it. So we multiply here. We get 1/3 x to the fifth e 1/3 x to the fifth e to the 3x. There's that product. Minus this integral, which we trade in for this product. So we get a minus 5/9 x to the fourth e to the 3x. And then we get plus this product, 20/27, and x cubed e to the 3x, right? Next one down is going to be 60/81, so minus 60/81 x squared e to the 3x, so minus 60/81 x squared e to the 3x. Okay, next one down is going to be plus 120/243 e to the 3x, and then we have minus 120/729. 120/729. Oh, let's see. This was supposed to be 120x e to the 3x. There we go. E to the 3x. And then plus the integral of 0, but the integral of 0 is just a constant. So I've got it. You can check it. Now, one thing I would want to do would be to reduce these. For example, 3 goes into 81, but it also goes into 60. This is 20. 81 divided by 3 is 27. Now there aren't any common factors there. 3 goes in here 40 times, and 3 goes into 243 81 times. This is all 3's. It doesn't have any 3's in it, so okay. And 3 goes in here 40 times, and it goes into 729 243 times. So I should reduce them, but other than that, I'm done. I'll let you check this and make sure that taking the derivative of this actually does give you the correct answer. When there's a lot of computation involved, it never hurts to check your work to make sure that you have the correct answer. And in this case, we can just do that by taking the derivative. Let's do another example. This one is similar as well. We need to pick a part to differentiate and integrate. Now, as we start this, it doesn't really matter either one, right? Sine, whether you differentiate or integrate, is going to give you some kind of cosine, plus or minus. And e to the x is easy to differentiate and integrate. It's always the same thing. So let's just put the sine over here. We could do it the other way as well if you like. Okay, so let's see. We differentiate the sine, and we're going to, because of the chain rule, the derivative of the outside is cosine. Evaluate the inside times the derivative of 2x is 2. So we have this extra 2 from the chain rule. We integrate e to the x, and we've got e to the x. So it seems like the integral hasn't gotten any simpler, right? We had the integral of sine against e to the x. Now we're just trading it in for the integral of cosine against e to the x. So maybe we should try integration by parts again. I'll integrate on this side and differentiate this. Let's see, the derivative of cosine is negative sine, and then the chain rule is going to put an extra 2 out here, so I'm going to have negative 4 sine 2x. Can you see that we're back to essentially the same kind of integral that we started with, up to a constant, right? We're going to have the integral of sine 2x against e to the x, trade it for this integral, which we then trade for this product and this integral. We're going to have to end up integrating sine 2x e to the x. So it looks like this is kind of frustrating, right? The integral didn't get any easier, it just kind of came back to us. But watch what we can do when we get a repeat like that. Let me just go through the pattern here. We have my plus and my minus and my plus. So we have sine 2x e to the x, and then we have minus 2 cosine 2x e to the x, and then we have plus the integral of minus 4 sine 2x e to the x dx. Okay, so we started with the integral of sine 2x e to the x. We got some product stuff, and then we have basically up to a constant that same integral coming back to us. Well, here's what we can do. Since this integral is present on both sides, why don't I just add this one to this side? If you pull out that 4, you've got 4 times the integral you want to find. So let me just put it over on the other side. I'll have sine 2x e to the x dx plus 4 times the integral of sine 2x e to the x dx. And then we have sine 2x e to the x minus 2 cosine 2x e to the x. So we have one of the integral we're looking for and another 4 of them. That makes a total of 5 times the integral of sine 2x e to the x dx equals the sine of 2x e to the x minus cosine 2x e to the x. And this is what I'm looking for, just the integral, not 5 times the integral. So I'll divide everything by 5, both sides by 5, in my equation here. Let's see, dividing by 5 is the same thing as multiplying by 1/5. So we have... Now here's some place where you might get tripped up. Don't forget to add your plus c, as there's not much there to remind you. But then this is the solution to the problem. Now, I'd encourage you to do this. Try it the other way. What if you decide to differentiate e to the x and integrate the sine 2x part? As you go through it, it may look a little bit different, but by the time you'll still notice that the same integral eventually repeats, right? Because you integrate sine once, and you get negative 1/2 cosine 2x. You integrate that again, and you get negative 1/4 sine 2x. So the numbers are a little bit different because we've put things in different places. But if you walk through it, you're going to get the same answer in the end, which is kind of cool. So by the time you end up getting this two integrals over on the side and then dividing by that constant or multiplying by the reciprocal of that constant, you should get the same thing. So check that and make sure that it works.